Distribution transformers are essential components of the electrical power grid. They perform the critical function of stepping down the voltage from high-voltage transmission lines to a lower, more usable voltage suitable for homes and businesses. The primary reason for employing these transformers lies in minimizing power loss during the transmission of electricity. Electrical power is lost in transmission lines due to the inherent resistance of the wires themselves. This loss is proportional to the square of the current flowing through the wires. To reduce power loss, the power companies transmit electricity at very high voltages. However, it is not practical or safe to directly supply such high voltages to residential or commercial consumers. High voltages can be dangerous, posing a significant risk of electrical shock and arcing. Arcing occurs when electricity jumps across an air gap, creating a dangerous spark. Distribution transformers act as an intermediary, stepping down the high transmission voltage to a safer and more manageable voltage level for local distribution. A typical distribution voltage might be 12,000 volts, which is then stepped down to 240 volts or 120 volts for residential use. The operation of a distribution transformer relies on the principles of electromagnetic induction. A transformer consists of two or more coils of wire, electrically isolated but magnetically linked. These coils are wound around a common iron core. The coil connected to the high voltage side is called the primary winding, and the coil connected to the low voltage side is called the secondary winding. When alternating current flows through the primary winding, it creates a magnetic field in the iron core. This magnetic field induces a voltage in the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. For example, if the primary winding has 1000 turns and the secondary winding has 100 turns, the voltage will be stepped down by a factor of 10. If the primary voltage is 12,000 volts, the secondary voltage will be 1200 volts. Distribution transformers are designed to be highly efficient, typically operating at efficiencies of 98% or higher. This means that only a small percentage of the electrical power is lost in the transformer itself. The losses in a transformer are due to various factors, including the resistance of the windings, hysteresis losses in the iron core, and eddy current losses in the iron core. Hysteresis losses are caused by the energy required to repeatedly magnetize and demagnetize the iron core. Eddy current losses are caused by circulating currents induced in the iron core by the changing magnetic field. Distribution transformers are typically oil-filled to provide insulation and cooling. The oil acts as an electrical insulator, preventing short circuits between the windings. The oil also helps to dissipate heat generated by the transformer losses. The oil circulates through the transformer, transferring heat to the tank walls, which radiate the heat into the surrounding air. Distribution transformers are typically mounted on poles or pads. Pole-mounted transformers are used to serve overhead distribution lines, while pad-mounted transformers are used to serve underground distribution lines. Pad-mounted transformers are enclosed in a tamper-resistant enclosure to protect them from vandalism and unauthorized access. Distribution transformers are rated in kilovolt amps, which is a measure of their apparent power capacity. The kilovolt amp rating indicates the amount of power that the transformer can deliver without exceeding its temperature limits. Distribution transformers are designed to operate continuously at their rated kilovolt amp capacity. The size of the distribution transformer depends on the load that it is expected to serve. A small residential transformer might be rated at 25 kilovolt amps, while a large commercial transformer might be rated at 1000 kilovolt amps or more. Distribution transformers are an essential part of the electrical power grid, providing a safe and efficient means of delivering electricity to homes and businesses. Without distribution transformers, it would not be possible to transmit electricity over long distances without incurring significant power losses. The selection and application of distribution transformers are governed by various industry standards and codes, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Code, or NEC. These standards ensure the safe and reliable operation of these critical components of the power grid. The IEE standards provide guidelines for the design, testing, and performance of distribution transformers. The NEC provides requirements for the installation and wiring of distribution transformers. Proper grounding of distribution transformers is essential for safety. Grounding provides a low impedance path for fault currents to flow back to the source, which helps to protect people from electrical shock. The NEC specifies the requirements for grounding distribution transformers. The secondary windings of distribution transformers are typically grounded to the neutral conductor. The neutral conductor is connected to earth ground at the service entrance. This grounding system helps to ensure that the voltage on the secondary windings remains at a safe level. The NEC also requires that distribution transformers be protected by overcurrent devices such as fuses or circuit breakers. Overcurrent devices protect the transformer from damage due to overloads or short circuits. The overcurrent devices must be sized appropriately for the transformer's kilovolt amp rating. The installation of distribution transformers must comply with all applicable local codes and regulations. These codes and regulations are designed to ensure the safe and reliable operation of the electrical power grid. Regular maintenance of distribution transformers is essential for ensuring their long-term reliability. Maintenance activities include inspecting the transformer for leaks, checking the oil level, and testing the installation. The oil should be tested periodically to ensure that it is free of contaminant. Contaminated oil can reduce the transformer's insulation strength and cooling capacity. The bushings in the transformer should also be inspected for cracks or damage. Damaged bushings can lead to electrical failures. The connections to the transformer should be checked for tightness. Loose connections can cause overheating and arcing. Distribution transformers are a critical part of the electrical power grid. Proper selection, installation, and maintenance of distribution transformers are essential for ensuring the safe and reliable delivery of electricity to homes and businesses. There are different types of distribution transformers. Single-phase transformers are used to serve single-phase loads such as residential homes. Three-phase transformers are used to serve three-phase loads such as commercial buildings and industrial facilities. Three-phase power is more efficient than single-phase power for large loads. Distribution transformers are also classified by their insulation type. Oil-filled transformers are the most common type of distribution transformer. Dry-type transformers are used in applications where oil is not permitted, such as indoors or in areas with environmental concerns. Dry-type transformers use air or other gases for insulation. Distribution transformers are also classified by their cooling method. Self-cooled transformers rely on natural convection to dissipate heat. Forced air-cooled transformers use fans to blow air over the transformer to increase cooling capacity. Water-cooled transformers use water to cool the transformer. Water-cooled transformers are typically used for large transformers in industrial applications. The efficiency of a distribution transformer is an important factor to consider when selecting a transformer. A more efficient transformer will save energy and reduce operating costs. The efficiency of a transformer is typically expressed as a percentage. A transformer with an efficiency of 98% will lose 2% of the power that it is transferring. The losses in a transformer are due to various factors, including the resistance of the windings, hysteresis losses in the iron core, and eddy current losses in the iron core. Distribution transformers are designed to operate continuously at their rated kilovolt amp capacity. Overloading a transformer can cause it to overheat and fail. It is important to select a transformer that is sized appropriately for the load that it is expected to serve. The impedance of a distribution transformer is an important factor to consider when coordinating overcurrent protection. The impedance of a transformer limits the amount of fault current that can flow through the transformer. This allows overcurrent devices to be sized appropriately to protect the transformer from damage due to overloads or short circuits. The inrush current of a distribution transformer is a large transient current that flows when the transformer is first energized. The inrush current can be several times the transformer's rated current. It is important to consider the inrush current when selecting overcurrent devices to protect the transformer. Distribution transformers are a valuable asset to a power company. These require regular maintenance. Maintenance includes testing the oil for contaminants and dielectric strength, inspecting the bushings and connections, and checking the overall condition of the transformer. Regular maintenance can help to extend the life of a distribution transformer and prevent costly failures. When a distribution transformer fails, it can cause a power outage. Power outages can be disruptive and costly. It is important to have a plan in place for dealing with power outages. This plan should include procedures for restoring power quickly and safely. Distribution automation systems are being used to improve the reliability and efficiency of the electrical power grid. Distribution automation systems use sensors, communication networks, and computer software to monitor and control the distribution grid. These systems can automatically detect and isolate faults, restore power to customers, and optimize the flow of power through the grid. Smart grids are being developed to modernize the electrical power grid. Smart grids use advanced technologies to improve the efficiency, reliability, and security of the grid. Smart grids include features such as smart meters, advanced sensors, and communication networks. These technologies can help to reduce energy consumption, improve grid reliability, and integrate renewable energy sources into the grid. Renewable energy sources, such as solar and wind power, are becoming increasingly important. These sources of energy are intermittent, meaning that they do not always produce power when it is needed. Distribution transformers play an important role in integrating renewable energy sources into the grid. Distribution transformers can be used to step up the voltage from renewable energy sources to the distribution voltage level. This allows renewable energy sources to be connected to the grid. Energy storage systems are also being used to integrate renewable energy sources into the grid. Energy storage systems can store energy when it is available and release it when it is needed. This helps to smooth out the intermittent nature of renewable energy sources. The electric power grid is constantly evolving to meet the changing needs of society. Distribution transformers will continue to play a vital role in the electric power grid for many years to come. Advancements in transformer technology are leading to more efficient, reliable, and environmentally friendly transformers. These advancements will help to ensure that the electric power grid can continue to meet the growing demand for electricity. One aspect to consider is the audible noise emitted by distribution transformers. While designed for quiet operation, transformers can produce a humming sound due to the vibration of the core steel caused by the alternating magnetic field. This noise can be more pronounced in certain types of transformers or under heavy load conditions. Manufacturers are continually working to reduce transformer noise through improved core designs and vibration damping techniques. Also, the location of a distribution transformer can impact the surrounding environment both aesthetically and in terms of potential environmental concerns. Utilities carefully consider the placement of transformers to minimize visual impact and comply with environmental regulations, particularly regarding the handling and disposal of transformer oil. Furthermore, the increase in integration of distributed generation, such as solar panels and wind turbines, into the electric grid is changing the way distribution transformers are utilized. These distributed generation sources can feed power back into the grid, requiring transformers to handle bidirectional power flow. This can impact transformer loading and voltage regulation, requiring careful planning and coordination. It's worth noting that the lifespan of a distribution transformer can vary depending on factors such as operating conditions, maintenance practices, and environmental factors. Regular inspections and maintenance can help to extend the lifespan of a transformer and prevent premature failure. When a transformer reaches the end of its useful life, it must be properly decommissioned and disposed of in accordance with environmental regulations. This typically involves draining the transformer oil and recycling the transformer components. The proper disposal of transformer oil is particularly important to prevent environmental contamination. Distribution transformers are a complex and essential part of the electric power system, playing a critical role in delivering electricity to homes and businesses. Understanding their function, operation, and maintenance is crucial for ensuring a reliable and efficient power supply. As technology continues to evolve, distribution transformers will continue to adapt and play a key role in the future of the electric grid. In addition to the points above, it's important to acknowledge the advancements in transformer monitoring and diagnostics. Modern distribution transformers are often equipped with sensors and communication capabilities that allow for remote monitoring of key parameters such as voltage, current, temperature, and oil level. This data can be used to detect potential problems early on and prevent failures. Diagnostic tools can also be used to assess the condition of a transformer and identify any underlying issues. These tools can help to extend the lifespan of a transformer and improve its reliability. The use of smart grid technologies is also transforming the way distribution transformers are managed. Smart grid technologies enable utilities to remotely control and optimize the operation of distribution transformers. This can help to improve grid efficiency, reduce energy losses, and enhance grid reliability. For example, smart grid technologies can be used to automatically adjust transformer tap settings to maintain optimal voltage levels. They can also be used to detect and isolate faults quickly and efficiently. As the electric power system becomes more complex and interconnected, the role of distribution transformers will become even more critical. Distribution transformers will need to be more flexible, reliable, and efficient to meet the changing demands of the grid. Ongoing research and development efforts are focused on developing new transformer technologies that can meet these challenges. These technologies include advanced materials, improved cooling techniques, and smart grid integration capabilities. The future of distribution transformers is bright, with ongoing advancements promising to improve their performance and reliability. These improvements will help to ensure that the electric power system can continue to deliver affordable and reliable electricity to homes and businesses for many years to come. It is also important to remember the safety aspects relating to working near distribution transformers. Only qualified personnel should work on or near these devices, and they should always follow proper safety procedures. Electricity is dangerous, and it is essential to take precautions to avoid electrical shock or other injuries. Utility companies invest heavily in safety training and equipment to protect their workers and the public. Public awareness campaigns are also conducted to educate people about the dangers of electricity and how to stay safe around power lines and electrical equipment. By working together, utility companies, communities, and individuals can help to ensure a safe and reliable electric power system for everyone. The electric power grid is a vital infrastructure that supports modern society. Distribution transformers are an essential part of this infrastructure, and their reliable operation is critical for ensuring a stable and prosperous economy. Continued investment in transformer technology, maintenance, and safety is essential for maintaining a reliable and efficient electric power system.